Okay, good morning. Good morning, everyone. Or good afternoon, depending on what when is your noon lunch. So anyway, it's my pleasure today to introduce Paco Najarro. Paco has come to visit us from the Centro Astrofísica in Madrid. He is actually, I've known his name long before I got to know him. I knew his name from working on the Galactic Center because he worked on massive stars there. He did his PhD in Munich, at the University of Munich, at the Universitätssternwarte Observatory of Munich with Rolf Kudrycki and Reinhard Genzel, so two very strong names in astrophysics. Then I think you got it in 1995, he got his degree. He then had some postdoc years as well in Munich, and finally moved to Madrid to the Instituto de Física de la Materia, and then he became a Ramón y Cajal in the first call for Ramón y Cajal. And finally, I don't know when you became a científico titulado, profesor.
I don't know, 2005 or so.
And now 2020. He's at the Centro de Astrobiología. I appreciate very much the work that Paco does, and he's very good at explaining, and he understands the details from atmosphere modeling to how you observe stuff and the problems of extinction, so you can really learn a lot from him. And finally, I would also say that he's responsible for me being here in Spain, so it's, he played a vital role there, so thank you very much, Paco.
Okay, thanks a lot, Rainer, for inviting me, also to Pepe, who talked to proposed me to come here and visit you. I'm gonna talk about multi-wavelength view of massive stars. For those, I mean, this is gonna be more like a sort of lesson on what can we learn from about the properties of massive stars in the different wavelength ranges, and the need to go multi-wavelength just to understand and get a handle of most of the properties of these stars and what can we learn. They're also important if we look at, for instance, at regions like the galactic center, due to the high extinction, most of the, the whole UV light, optical and UV light, which most of the massive stars have their maximum of SEDs, is hidden by 30 magnitudes of extinctions, which means that only 1 in 10 to the 12 photons reaches you, which is hard. And you want to understand different wavelength domains, what you can obtain from the massive stars, just to look for consistency and to be sure that if you analyze and study these stars for instance, the infrared, the results you get will be consistent with those obtained from the optical or the UV or even radio. So the aim of this talk is just to first introduce you to how massive stars work and how important they are, and basically go range by range, trying to learn what we can get, which wavelength domain is best at to obtain information about the properties of these stars, and then just put it all together and see how far we can get in understanding these subjects. So basically, the outline of the talk is why going multi-wavelength, and the aim is to best constrain the stellar properties of these objects. Massive stars for are any stellar object with masses above 15 solar masses, more or less, up to 150, or the so-called, which are very fashioned nowadays, the very massive stars that are being claimed to have masses in the LMC, for instance, at the core of the Tarantula Nebula, stars with masses about 300 solar masses, initial mass as they were born. It's still a claim that they may be not that massive, but it's a huge range of masses. And if you remember from astrophysics lessons, there's a relation between the mass of the star and the luminosity. Of course, when you go to very high masses, this relation changes, but basically you have that the luminosity of the star goes as a power of 3 of the mass. So basically, a star with 100 solar masses will be 1,000,000 times more luminous than our sun, which is, it tells you that you can use the stars as even standard candles because it will be so luminous and you can observe them individually in galaxies in the local group and maybe beyond. So there are studies going for that, so they are very important for those issues. These massive stars, the very massive ones, when they all explode as supernovae, when they are very massive, they can leave behind a black hole, magnetars, all kind of sort of exotic objects that were very fashion nowadays and can help you understand very high energetic phenomena that are observed in astrophysics and very important today. So the problem with massive stars is that if you go for cool stars, everything works in the so-called local thermodynamical equilibrium approach. That basically, if you know the density of electrons and the temperature, you can obtain all the populations of the different levels of the elements, of the ions, and you can obtain a very straightforward spectrum of the star, and it's easy to compute. Is what Kuruts did, and it's very simple. However, in the case of massive stars, there's a problem. You enter the regime of non-local thermodynamic equilibrium, and you need to compute and to obtain the populations of your the levels of your ions. You need to solve the statistical equilibrium equations together with the radiative transfer equation, the equation of energy, and this is much more complicated. That takes time, so these subjects are much more difficult to model and analyze than other things. You can also imagine that these stars also have strong stellar winds. So contrary to our classical stars where everything happens within a scale height, it's very close to the photosphere, there are phenomena in these massive stars that take place close to the photosphere at, let's say, velocities below the sonic point, while there are a lot of lines which are forming the stellar winds and have contributions up to 3,000 kilometers per second, or even hundreds of stellar radii. So you have to consider a huge domain in stellar radii and zones compared to the classical way we use in other later time styles. You can also imagine that for that reason, a plan parallel approach breaks down and you need to go to a spherical symmetry, which complicates a little bit more the whole picture. So basically what we want to have is to obtain parameters like the effective temperature, the gravity, the mass loss rate, which characterize the stellar wind, how the velocity takes off from the wind and reaches its terminal velocity. This is called the velocity field. Massive stars, all these stellar winds are caused by transfer of momentum of the photons. You have a lot of resonance lines. A resonance line, if you remember, is a line in ions arising from the fundamental level to a nearly excite level. So basically, you have a lot of material that can absorb that line, and so if a photon comes, it just communicates its momentum to the ion gets accelerated and distributes its momentum to the rest of the bulk of the mass, and therefore through transfer of momentum you get a wind acceleration and a mass loss, and that's how you generate stellar winds. You need to look for homogeneities, which is called clamping. Contrary to what it was thought at the beginning, the winds of these stars are not homogeneous. They have like little clumps, and some of them are optically thin, some of them are optically thick, and you have to handle that, and you have to take that into account. And of course, if you want to characterize your star, you need to know the abundances of the main elements like helium, and I put Z to constrain iron and also CNO elements and whatever. So this is what we want to find out. We will see, and this is what we will try after this short introduction. What are the pros and the cons of individual wavebands? We will go for the UV, then the optical, and then the infrared and the radio. And as I said, we will have a look at how can we obtain information from each of the wavebands. Let's, at the end, go for consistency stuff, multi-wavelength, but let's just move to the UV. These are HST spectra of massive stars in Cygnus OB2. This is a huge star forming region, or open cluster, which is has a lot of O stars, and the characteristics you see is that this UV spectra, even if it's extincted, it's only 1.7 kiloparsecs away, but you can clearly see these P Cygni lines, which are the characteristics of massive stars. If you analyze those P Cygni lines, it's obvious that basically the star will absorb photons up to the terminal velocity. So these UV lines, which are forming these resonance lines, are going to give you information about the velocity field and the terminal velocity. So you can see lines from nitrogen 5, silicon 4, or carbon 4 here. And if you just get one of them, you can really do a very simple fit of the P Cygni profile, and this gives you a very rough, good estimate of the terminal velocity, and this beta parameter, which tells you the shape of the velocity field, how fast or how slow this the material is accelerated into the wind. A low beta will mean the material gets accelerated very fast. A high beta means it takes longer. So, and this beta controls the width of this line, and basically the point up to you can observe gives you a measure of the terminal velocity of the wind. So what you learn from here is that basically from the UV, you're very good at obtaining information about the velocity field. So what happens with the other parameters? If you look at the other parameters, you look, for instance, at the mass loss rate, here you have an analysis of two optical lines which are classically used for massive stars. This is the helium-2 4686 line, is between level 3 and 4 in the helium-2 biome. This is H-alpha. I guess most of you know it's the 3 to 2. And here you see two different models with completely different mass loss rates. And you see that the optical lines are fairly insensitive to that. You can change the mass loss rate by a huge factor, nothing changes. However, in the UV, you see a huge change between the blue and the red ones, the red one being a model with a much higher mass loss rate. So this tells you that the UV, the optical is not the way you should go if you look for, at least for low mass loss rates. You need to go to a very high mass loss rate to start seeing effects here, while the UV reacts immediately and you can get very sensitive to mass loss rate. So maybe the UV is, in principle, could be a good domain to obtain estimates of mass loss rate. However, there's a problem with that, and this is clamping. The same spectra or the same mass loss rate that was obtained for instance, for the UV lines, these carbon 4 or the silicon 4 lines, when applied to the so-called optically, not saturated lines, gives you this kind of spectrum, this kind of lines, which is completely overestimating the mass loss rate of the object. So if you would have to fit this line individually, you will have to sink the mass loss rate value by a lot. If you reduce it, you will get that. Remember that the resonance lines, by definition, are proportional, are linearly dependent with the density, with rho, while the recombination lines like H-alpha or the infrared continuum flux or the radio flux, which is free, is rho squared, because you're multiplying number of ions by number of electrons. So this is what you get. So in principle, what happens is that if you look at these unsaturated lines, you need to sink a lot the mass loss rate. But if you use that and you look for radio, then you get a discrepancy. So clamping, in a sense, I mean, you know that basically we always relax all our assumptions, and we meet these problems, we need to recall something like many of you who have done analysis know about microturbulence or all sorts of fudges that spectroscopics invent to get rid of those problems. So clamping is just an issue to be able to distinguish between linear processes which depend linear with rho, which remain unaltered by microclamping, and processes that go with rho squared, which are recombination, for instance, that depend a lot on clamping. And that's one way to reconcile these differences. So basically, you will need to reduce this, which means increase the clamping to match the recombinations lines where you will miss this stuff. I will skip this. And I'll move to what is known as the weak wind stars. And there's another thing it's another problem with the UV. Weak winds are, in principle, a theory of radioactively driven winds will give you an estimate of the amount of momentum that is transferred to create the wind of these stars. And when one goes below in the galaxy, and in the LMC is a bit higher, for instance, but when one goes to this below this value in the luminosity of the star, it just looks at observed objects and realizes that the mass loss rates that are derived from the UV are much too low. It's like these objects cannot produce the expected amount of mass loss rate, and this is an open issue. So here you have an O9 dwarf, a star with a luminosity a bit below this point. Black out the observations, and what you see here is that this object is a pure absorption with no wind, and the same, this is the blue one, you increase the mass loss rate by a factor of 4, which means going from the blue to the red. So basically, if you would rely only on mass loss rate, I would say, okay, my mass loss rate is this one, which more or less reproduces what I see here. But it turns out that if you put X-rays and increase the X-rays, you could have a factor of 4 more mass loss and still get the green one, which coincides with the blue one. So basically what this is telling you is that if you don't know the X-rays, there's an X-ray mass loss degeneracy. And that's very important, and that happens, and I can show you here. Here you have all sorts of UV lines. Look at here. The mass loss rate is increasing by almost 2 decks, and you cannot tell anything about which is the correct one if you don't fix the X-rays. So unless you fix and you know how the X-rays look like in your star, then you may have a problem if you want to use the UV, which is the classical diagnostic for mass loss rate. So this is important, and people has to be aware of. Of course, the UV, most of the massive stars, especially O stars, B stars have already in the optical some iron lines, but the O stars have in the optical there are no iron lines. So if you want to get a handle of the true metallicity, which is the iron content, you have to go to the UV spectra. So here you have a UV spectra of a star in the galaxy, and here you see this thing that looks like noise. These are thousands of iron 5 lines that are merged here. This is iron 4, and of course, the more iron you have, the deeper these features will be. If you go to the LMC, which has a little bit less metallicity, if you compare, get weaker, and if you go to the SMC, basically you see nothing. So we're going to galaxies, dwarf galaxies in the beyond, almost 1 megaparsec. These stars are very bright, as I told you, so you can observe them. And then it turned out that from H2 region analysis, from oxygen line analysis, it turned out that this galaxy had to be below 1/10 solar from the oxygen content. The SMC is 1/5. And if you look at the iron, it looks like at least has the same quantity of iron as the SMC, and maybe it's between the SMC and the LMC. So this is very important. This is telling you that maybe these dwarf galaxies, these dwarf spheroidals, they were evolving not like our Milky Way in a sense, and they were producing the classical iron, which is produced by the low mass stars, while the alpha elements, which is the oxygen and is the one that was being measured from the H2 analysis, and this is made by O stars, was less because these small galaxies were not able to produce so many massive stars as, for instance, the standard, which is our comparison, which is our galaxy or the sun. So basically you have a kind of alpha versus iron element decoupling. So in this case, what you have is a dearth of massive star formation in these galaxies. You can go, for instance, to places like the galactic center, which is the other way around. Because of huge massive star formation, your IMF looks like more top heavy, so that you produce, in comparison to other places, many more massive stars, which will provide you much more oxygen. So in this case, you would expect the alpha elements like oxygen, silicon, magnesium to be enhanced with respect to iron. And we will see later whether that's the case or not. Okay, so this is very important, and it is very helpful. I will skip the problems with the turbulence, because otherwise it will take too long. But basically, what I'm saying is that, as well, in a classical O star, here's a very high resolution HST GHRS spectra of 10 lakh, where you can see almost the individual lines of iron. The only difference between these two models is the microturbulence velocity. And you can clearly see that in an O star, it's very easy, or more or less tentative, to describe the continuum. Here's an LBB. P6 is the classical LBB. And here's the UV flux. So, I mean, there's no way to place a line where you could see, like here, where you have several points where you can place a continuum, and here there's no way. So sometimes, if you want to analyze these kind of stars, it's maybe you would make a lot of errors if you try to normalize the spectra, because if you don't know whether the continuum is, it's going to be very hard, and you could make a lot of errors. So most of the time, the best thing to do is just to compare your absolute flux distribution, which is, and just rewrite it and comparing it. That's the way it works. So basically, just summarizing, UV studies for the temperature, you can use normally the iron ionization stages. You know, anyone who has done any spectral modeling, you know that the best way to determine temperature is to use two different ionization stages from the same ion, because if you increase temperature, one is going to go up and the other is going to go down, so the sensitivity is going to be bigger. In the case of the UV, you can use iron, which is not too great, and for not too dense winds, you can use these photospheric lines, but it's not too accurate. So basically, I will, whenever I describe how to obtain the parameters for all these stars, I will give you green like perfect, red like shit, and orange like maybe, yeah? Okay, so in a sense, for me, in the UV, if you want to get parameters for a star and look for temperature, it's going to be very orange-like. Log G is complicated. Most of the lines are going to be very insensitive to log G, and it's going to be hard to get a good distribution. So what is UV good for? From what we've learned, it's good for V infinity, it's good for estimating m dot and clamping, and the way, the shape of the velocity field. It's not very good for effective temperature or determining the mass of the objects. And we've seen that for iron is maybe the best way. So for abundances, it's okay, but of course, you have to be aware of things like microturbulence and X-rays if you want to make a nice estimate of what's going on. Let's move to optical. So this is where everyone started. The stars are very bright. They have, in the optical, you can see all the Balmer lines, the helium-1 and the helium-2 lines, which are the classically used to determine temperature. And you know that the Balmer lines, because of the Stark effects, in the case of, are very sensitive to the gravity. And therefore, these spectra, the optical is going to be probably the best way to get a handle of the masses of the stars, at least from the spectroscopic studies. Here's a description of the method that people in the IAC use. Basically, you make a huge grid of models, you get your observations, you clip the zones in all, these are the Balmer lines, these are the helium-1 and the helium-2 lines, and basically you clip the zones that you want to fit, you do a chi-square fit and get this kind of minima, which give you estimates in your chi-square fit of the temperature, the gravity, the helium abundance, microturbulence, and other parameters. So this is one approach. Another approach is to use a genetic algorithm method. Those are like brute force. You compute like 70,000 models. If your code can go very, very fast, this is one. It's using FastWin, or the fastest codes for massive stars. But otherwise, they yield more or less similar parameters. And the optical is well suited for effective temperature, as we've seen, because you have helium-1 and helium-2. If you go to later types like O9s, B stars, you can use simultaneously helium-2, helium-1, plus the silicon 4, silicon 3. Or if you go to very, very hot O stars, where the helium-1 is gone, you have to rely on other ions. And the best ions to determine the temperature are the lines of nitrogen. Nitrogen 4 and nitrogen 5, those are giving you the temperatures. And it's sometimes people try to get a single fit, either with the nitrogen, with the helium, and sometimes you're happy if they're consistent, but sometimes there are differences by several thousand degrees, and that may be a problem with your models and a problem with the kind of approach you're using. So this is basically one of the messages you have to go home with, is that we're not happy with what we fit. We were very happy with what we don't fit. So that this is giving us information about what needs to be investigated. So, of course, you can see here that there's no trace of mass loss, there's no emission, no PCNE profile, so obviously you cannot get a handle of the terminal velocity, nor the wind parameters, nor the clamping, at least for this kind of stars. And this is again a plot from our review in 2008, where you can move your mass loss rod. This is the same star. The only thing we are doing is just many models. This is H alpha, which is the classical optical line that some people use to get a handle of the mass loss rate. You go from 5×10 to the minus 10 solar masses per year to 1×10 to the minus 7, and basically for over almost 2 decades you get insensitivity. It's only about when you get 1, 2, 3 here, 5×10 to the minus 8, that you start to see something moving in the core. So this is telling you that if your star is going to be a dwarf, forget it if you want to obtain mass loss rate. It has to be more like a giant or supergiant with higher mass loss rate to start to see some effects if you only have optical spectra. So H alpha is not an optical mass loss rate diagnostic. Let's move then to the infrared. This is what I told you before. This is the classical SED of one O star. So because of the temperature, the peak of the flux takes place in the UV. That's why we can use HST and go very far away to almost 1.4 megaparsecs and get UV spectra of individual stars. But if you go to, for instance, to the galactic center or through the galactic plane, their extinction starts to kill you. So this is how the SED of your star, for comparison, this is a black body, okay? And this is the so-called free and bound-free emission coming from the stellar wind. So if you go to already 10 magnitudes of extinction, basically you get no flux here, and the peak of your star moves to the J band. And if you go to a place like the galactic center where you have at least, or maybe 30 magnitudes of visual distinction, everything, even in the K band, your spectrum is very red. And if you try to measure the J band at the beginning, you can count here like 4 decks less photons than in an unextended place. So this is a project we have with one of my students, and it's basically trying to get studies of clusters, massive clusters in the Milky Way. So this is a picture, this is the sun, this is the galactic center, and we've detected we've done multi-object spectroscopy, or not multi, it was done with ISA, so it was slit by slit measurements of the most massive stars in these clusters, basically try to understand whether we can characterize the stars and the metallicity in this cluster. That was his project thesis. And what you can see, for instance, you have Marzo 81. Here's one star. This has about 30 magnitudes of extinction. This is this guy here. So the sun is here, so it's on the other side of the bar. It's very far away. And with 30 magnitudes of extinction, you can only get the K and the H band. In J band, you would get basically nothing. So we can understand, get feeds to the hydrogen, the helium lines, and some of the carbon and nitrogen lines, and get estimates of the not only helium abundance but also the nitrogen and carbon and oxygen abundance. So summarizing, infrared, what about the temperature? The helium 1 and helium 2 lines are almost as good as the visual, so they are okay. So just assume we only had H band and K band spectra from one star. In principle, using the helium 1 and the helium 2 lines, we could obtain a very narrow and good estimate of the temperature. We can also use, if we have enough signal to noise, also metal lines. There's a problem with the massive stars. Massive stars are the stars that everyone uses as a standard in the infrared. A standard mean is, what a standard mean is that you can use something that is featured, has no features. Basically, it's flat. So if you really want to see the metal lines and you want to see the hydrogen lines, you really need a very high signal to noise, and you really need a very good reduction, because otherwise, basically your spectrum will be, a signal to noise of 30 or 50 is something you cannot do or start with to perform spectroscopy to derive metal abundances in our stars. So you really need to go very high in signal to noise. But if you do, you may use these lines and really get a handle not only in temperature but also in abundances. So for temperature, I would say infrared is good. For log G, it's a bit worse than the optical, and the reason for that is that the lines you normally use are the lines in the H band. In the optical, you remember we use the Balmer lines, the H series. The Balmer lines are the transitions from the ground levels from level 2 upwards. In the H band, you have the bracket lines. The bracket lines are coming where the lower level is number 4. The lines are a bit weaker, but still they are very sensitive to gravity. So you can use it. So in summary, infrared is good for effective temperature, log G, and dot and clumping. It's not so good for the V infinity, although the lines are better suited than the optical. And abundances is more or less than the optical. If you have high signal to noise, you can really obtain abundances, and which is very important if you want to characterize your clusters. So let's move on. I will just show you that in the infrared, contrary to the optical, where everything takes place more or less close to tau Rosland equals 2/3, because of the bound-free and free emission, the continuum, you have an extra excess of flux, which corresponds to basically having a stellar radius, which is a function of the wavelength. So if you have a strong massless rate, here you see 1 micron to 100 microns, and this is the area below these curves corresponds to the flux of the star, which can be characterized with an effective radius. So basically, the black line here is what corresponds to the optical and the very near infrared, and as you move towards higher wavelengths, then you have this infrared excess that makes your star look bigger. So you can imagine that normally when you look at spectra, you look at what is called the normalized spectra, which is your nu divided by your continuum. In the optical, classically, the continuum is the same. But in the infrared, you have to be very careful, because the continuum at 2 microns is going to be different from the continuum at 20 microns. So you're going to divide by something that is not the same. And this can be dangerous. So, in the case of in the infrared, in the case of weak winds, which is what we showed before, stars with very weak winds, you have that H alpha is very insensitive to mass loss, while bracket alpha, which is the line at 4, 5, is very sensitive. We'll talk about this later. And in the case of strong winds, because of perverse behavior of opacity, you start to have lines that really depart from the classical Gaussian profile. So you have, because of continuum opacity, you will have this here, and lines that, where if you observe this line, for instance, you will think, well, my radial velocity is wrong. No, it is because basically here you have so much opacity that you can only absorb very close to you, because the material behind you is fully absorbed. So, or behind the star, sorry. I will skip this, but basically to get back, this is the picture we showed before, the behavior of mass loss. Look at bracket alpha. So, as we said before, we can see that the core of bracket alpha, because of the strong effects of non-LTE in the infrared, is already by 510 to the minus 10 solar masses per year, you can start to see effects moving in the line profile, while in the optical is fully insensitive. So basically, what you see in the core of H alpha is done in the wings of bracket alpha, while the core is much more sensitive. So if you want to derive mass loss rates in weak wind objects, don't go to H alpha, go to the infrared. So the infrared is much more sensitive, and this is well known since 72. Mihalas talk about this, and this is very important because it's one of the only ways to really get a handle of the mass loss rate if you don't have UV, for instance. So, same with other stars. This is bracket gamma. Bracket gamma is the hydrogen line just sitting in the middle of the K band, and its behavior, in a sense, is almost identical to H alpha, to the line in the optical. And here you have the Fun gamma line, which is in the L band. It's the 5 to 8, which is much more sensitive and also can be used. So you can imagine that if you have K band and L band spectra with bracket gamma and the alpha and the Fun alpha and the bracket alpha lines, you could get a very good estimate of your mass loss rate and the effects that are taking place there, compared to our classical study in the optical. So the conclusion from these view graphs is that in the infrared, the L-band lines are probably the ones provided the best reliable constraints on the mass loss rate. Here's an example. This is Sigma Ori. This is a star, a dwarf. Here you see how the core of bracket alpha is nice. Here's H alpha, which is insensitive. But look at bracket alpha. This core is produced by this low mass loss rate, and you can get also the Fun gamma and some lines. So this, you can get a sensitivity of 210 to the minus 10, which is something that is never reached before. Okay. That was a weak wind. If you go for a dense wind star where everything is an emission, of course H alpha provides it, but also bracket alpha Bracket gamma is just in the way to turn it into, bracket gamma is just in the way to turn it into emission, so that's why it looks so noisy. But again, we get same consistency. So one of the important things, as we talked before, was clamping. Clamping, if you do a model without clamping, you will clearly see that you could match more or less H alpha and a little bit bracket alpha, but then you will have a severe discrepancy in these lines. However, if you introduce clamping, which is something that decouples the behavior of the density to the density square, then you can do a very nice match of these line shapes and reproduce everything simultaneously. So again, this is telling you that, I mean, even if it's been ignored because detectors took a long while to develop, the infrared is a gold mine, it's a treasure to get information from. So, in the infrared, let's summarize: bracket alpha, bracket gamma, phone gamma. They are very good traces of Adam dot, and the next step is just to see how can we combine the whole thing in. I will show you just very fast. I don't want to bother you more. A couple of examples where you put all together and see whether consistency is reached. So we want to go multi-wavelength. This is a classical case. This was in my thesis. This is P Cygni, and what we found in this star is that you could do the optical, and then before ISO was launched, we said, okay, we've done optical analysis. With these parameters, we should get the infrared stuff. And then we found out that when the ISO data came, the optical model was very good at reproducing optical and all lines beyond 10 microns, but in the region between 2 and 10 microns, our models severely overestimated the observed profiles. And the solution for that is what I told you before. Basically, in the infrared, you're observing line over continuum. The lines were all formed here, but the continuum forms here in this region. So just by changing the velocity law, just by changing the way the velocity is accelerated, you change the continuum. You don't change the line, but you change the continuum as you plot the normalized one, then you can reproduce it. So again, this is telling you that the infrared is perfect, not only for lines, but also sometimes for continuum, where the optical is little information available from. Okay, I will skip the analysis for PSIC. I will just show you an example of what can we do, the level of accuracy we can achieve now. This is an example of the pistol star in the quintuplet, one of the LBBs, and here you can see how you can do with high resolution and high signal to noise. You can get estimates of the iron lines, estimate of the silicon lines, which are alpha elements, and also the magnesium lines, which are equally alpha, it's an alpha element, and therefore you can get a direct estimate of your alpha versus iron. And this is very important if you want to understand what has been going on in the star formation history of the region. If you have a high alpha, it means that for some reason there was a preference to form, at least in not so latest past, to form a lot of very massive stars, or more massive stars than in the north, in the surroundings of the solar neighborhood, because you would get more alpha elements, because you need all these supernova to be exploding and providing more alpha, and then having to wait to the later type stars, which are the main producers of iron. Okay. This is an example of what I showed you before of multi-wavelength. This is the HST with cos spectra of one O star in ISIN 13. This is our model of the UV data, and this is a model to the optical data obtained with force. So basically, we're just from this thing you cannot get any information about the mass loss, but from this you can get information about the mass loss and the winds of the stars. I will skip this. I will show you now a galactic star where we have everything. We have UV, optical, infrared, and radio. And this is one of the stars in Cygnus OV2. So what I'm gonna do is I'll show you what we don't fit, because it's the interesting stuff. The other things are not interesting at all. So basically, looking at the UV, basically everything fits perfectly, but the O5 line. And this is basically, or mostly, related to probably macro clamping. There are two kinds of clampings. I told before, the ones in which the clamps are optically thin, and this is could be related to the presence of optically thick clamps. Oxygen 5 doesn't fit, but oxygen 4 fits much better. So it's really nice to see this kind of effects. Here's the whole optical line. So you see all the hydrogen and some of the metal lines. They look carbon, nitrogen, H alpha, helium, perfect. But then this is the infrared. But then you see some lines in the near infrared that are, I will flag them out. This line is very sensitive to X-rays and to where the clamping begins. This line is a recombination line. It tells you that probably our model atom is not doing correctly. And this is a helium-1, a helium-2 absorption that is overestimated by our model. So basically, this tells you how we have to go back and work out in our models and in model atoms to see whether we're doing that correctly or not. So this is so far for optical and infrared, and let's go to radio. So this is a fit of the SED of our object. Here's 1 micron. So this is the only infrared. This is the optical. And then you extend it. This is some mid-infrared data. And then we go to Plateau de Bure, which is in the millimeter region, and we found this value. This one is an upper limit, but we could knock this value. And this, normally, if you look at massive stars, you look at massive stars, the spectral index that you expect in radio for a fully ionized wind is about 0.6. But if you have a clamping that is changing, or the wind is recombining, anything will make depart your spectral index from this value. So now you go to radio, and your wavelength distribution should go this way was 0.6. But basically, you see that this has to drop, and these are upper limits. We know that by no means the radio emission is going this. I mean, it's extending this way. It's much well below, which means that clamping has to be disappearing in the outer parts of the wind. And this is a Herschel data that I'll skip as well, but I will move to this. This is Zeta Papis. Zeta Papis. This is a representation of the clamping. If the clamping was constant, it will go up here, and then this is a representation of the clamping. It will be maintained constant over the region. But the models show that this is an empirical estimate, and this is a model done with hydro by Mark Runakers and Owoki. So basically, you see that it reaches a maximum and disappears. And if you place that in this flux distribution, this is the Herschel data. You see that without clamping disappearing, it will be like this, and with clamping disappearing, it is like this. So therefore, it seems to be the case that some of these stars, very probably the outer parts of the wind, are not clamped, or the clamping vanishes. So I will say this is one project we have with ALMA, and it's trying to look for recombination lines that are very weak. This is a hypergiant, and okay, this is about 0.2 over the continuum, but if you go to Zeta Papis, this is something you cannot do with ALMA just because of the bandwidth. You can see the winds are from the separation here is 4,000 kilometers per second, which is much broader, so it's almost impossible to cover. So if you want to do recombination lines in massive stars, you have to go to slower wind stars like LBVs or other stuff. Okay. By the way, look, it's the kind of sensitivity you will need to match it. It's only 2% over the continuum. Okay. So just let me summarize. We've reviewed a bit firstly what the potential of the different wavebands are. In the UV, if you want to do massive stars, you can be sure that will be good for estimating the velocity field and the clamping. From the optical is the best way maybe to get the gravity, which is the mass and the temperature of your objects. The infrared is good for basically everything, and it's also, just to emphasize that we've discovered that the lines in the L-band are maybe the best primary diagnostic tools to measure mass loss rates, even in the cases of weak wind stars from which no information is at the optical, and the information in the UV could be polluted by X-rays or microclamping. So we really need to go multi-wavelength. We see that in the picture I've shown you for this Cygnus OB2 star, that basically we can, or the pistol, you can obtain very consistent results in doing multi-wavelength. And it is clear there are zones that are needed to be studied, and for instance, only radio will be available for that. We don't know, the only way to get the behavior in the radio domain and on the outer parts of the wind for many of these stars is going to be going to radio. Otherwise, we'll lose this information. And I think that's it. Yeah, thank you.
Question. This has been tense, but
I have a very simple one. Is there some way of writing down a formula relating mass loss rate to the mass to put in evolutionary calculation?
No. There are formulas used for the evolutionary calculations. There are formulas used which relate the mass loss rate to the luminosity and the metallicity of the objects. Those are developed by Beauty Group and by Georg Fink and company. Basically, what you do is you solve all your momentum equations with all the lines, and as a function of luminosity, metallicity, just think that the lines which accelerate your wind are basically the CNO elements, but the lines that produce, that lift your wind and set the mass loss are the iron lines. So the less iron, the less iron content, the lower the mass loss that you're going to make. And those kind of formula are currently used in most evolutionary models. Even MESA, Geneva, the Bond Group, everyone's using that. So there's not to mass, but to luminosity. Because basically you have to think that it's momentum from transfer from the photons, which is driving your mass loss. So this is the direct connection.
So I have a question on a concrete slide to show in which time lag and another one.
Yeah.
And for the upper one, you show where the continuum should be. And my question is, how do you know this is the continuum?
Because it's a model calculation.
And with the model calculation, could you also?
When you do your model, you compute a spectrum with only the continuum processes, and a spectrum with all the line overlapping processes. So you get two flux distributions. You divide one by the other, and of course then you know whether your continuum is. In the case of 10 lag, I mean in the UV, so it's been always a nightmare trying to place the continuum just from the pure observational point of view, because there was always a kind of offset of minimum continuum absorption because of all the lines. So, but in our case, if we do, in the case of, I basically in the UV I never normalize. Because I use the true spectral distribution with absolute fluxes, and this is what I compare to the flux calibrated fluxes obtained from HSD, IUE or whatever. So all I do is just I apply an extension and I compare absolute values with Bretton values, and that's it. So, but in classical work, in no stars, for instance, in dwarfs, it's been used. But I will never trust a normalized UV spectrum.
For the lowest one, when you said that the continuum was not, so for the upper one, then not you would draw the line of the continuum, but you would also do the same for the second one.
Yeah, you could. Yeah, as I said, from the model, only from the model. From the observational point of view, you never know. You don't know if it's, I mean, by the half of the by crossing the top of the highest line, so it's half of it or not. You never know it in advance because you don't know the amount. I mean, you have so many lines that are like these were like beeps or like infrared and like very broad bands that sink the whole continuum. You don't know where you started. So only from the model you can estimate it.
Yeah, and for that reason, the question is how far above the spectrum lies the continuum?
Well, I would say that it would be, there were some lines that look like Piscini-like, so I would say by half, if it's pure Piscini, you know that pure Piscini is a pure scattering line, so the highest you can go is 1 over the continuum, so by half of that height. So between 0 and 2, so that would be 1, if you assume those are pure scattering lines.
Since you mentioned that companies vanishes with in the other parts.
No, this is a claim, yeah. Many people don't believe that and they don't use it.
Now, I was thinking, since also the stellar radius is increasing with lambda in the radio regime, infrared also, then which is in order, if this claim is true, which will be the best wavelength coverage for the observations in order to discriminate this effect of the compiness?
I'd say for most of the stars, it would be to take infrared spectra and to get partial and radio data.
Going to
most of the lines, I mean the strong recombination lines are going to be formed in the very outer regions as well. So it would be lines that will form in regions close, very similar to radio in the infrared, very strong lines. The continuum in the infrared as well is going to form very close to the photosphere. The continuum in the far infrared, in the 60, 70 microns, it will depend always on the muscle, but it will start to form in these intermediate regions. So basically, if you look at the curve of the clamping, you want to sample at all places. So there will be lines, strong lines that will sample the outer parts. There will be weak lines sampling the mid parts, and there will be very weak lines or continua in the near infrared. So basically, you need both continuum and line measurements to get a good radial sample of the way it behaves. In the case of radio, you're going to be only sampling for the most massive stuff. You're going to be sampling only the outer parts. But this is going to tell you whether you really need your clamping to vanish or not. There are other stars in the same cluster, like I think it's single solving 10, which requires no vanishing. So it's not universal. But basically, what you want is each star to be analyzed individually to see whether it fits one or the other approach. But this is the only way to obtain reliable Maxwell traits.
But these stars are isolated because the beam of the Herschel is very full.
Those ones, yes, those ones are isolated.
What is the evolutionary stage of this star?
Oh, those stars are supergiants, so they are, I don't know, 4 or 5 million years old, 3 to 5, some of them. So, and these are some of them are binaries, but basically, in most of the cases, they're not so far away, so that optical spectroscopy has been tracking them forever, so we know which ones are spectroscopic binaries, which ones have a component nearby, which could be contributing to something. But in most cases, for the Herschel data we have, they are compatible with the dominant source in the optical being the dominant source in the far infrared. So those are well separated. I mean, we could not do the kind of clusters I showed this picture of the galaxy with clusters around. There the stars are much closer, and of course farther away back Herschel would have picked many stars in the same beam. Those are 1.5 kiloparsecs away, so it's signal solitude, which is a really big cluster, and it's spread. I don't think it's a problem.
In the radio, one expects a spectral index of 0.6.
Yeah.
It won't have a constant velocity and constant ionization fraction.
Mm-hmm.
So a change in the velocity has the same effect on the spectral index that a change in the fraction of the ionization or probability. So how can you distinguish that you
of course.
have a change in the velocity?
I mean, you need to know the terminal velocity. You track, many of the stars have been tracked in the UV, and you can see that more or less the changes in, you look at the resonance lines in the UV, and you see that more or less within 10% the terminal velocity doesn't change. So you can think radio is something that happens to far away, that this beta component, which maps the infrared but not the radio, makes sure that by the time you reach the radio formation region, you have already reached your terminal velocity. So from the UV, you know that your terminal velocity doesn't change much. Basically, the changes in flux are not going to be significant. Then recombination. It depends on the kind of star you're using. Assume you use an O star. Okay, O star is going to have always the main contributor to the flux. It's going to be hydrogen, and then you will have 1/10% of this contribution is going to be by helium, because normally they're not helium rich, not yet. So if you recombine helium from, let's say you have helium double ionized to helium single ionized, the change in the spectral index is going to be maybe 0.0, from 0.6 to 0.67 or whatever, something like that, but not much. But now imagine you have an LBD, which is a star which has very thick winds, and the problem is that the temperature is lower. So basically what you're recombining is not helium, it's hydrogen. This is the case, for instance, of the Pistol star. This is the case, for instance, of P Cygni and many other stars with very strong winds. Their temperatures are about 18,000 K, but the wind is so thick that the whole Lyman ionizing flux doesn't manage to get through and ionize the whole wind, and at some point they recombine. Then the change in spectral index is brutal. Eta Caris was one example. You get a change in the spectral index from 0.6 to, our numbers work out that the kind of density distribution of the electrons and the ions goes, instead of 1 over r squared, which is the classical wind with the equation of continuity, it goes to 1 to 3.5, and that turns on into an spectral index which is 1.3, which is what we observed in P6, for instance. So that's a problem, that's an issue.
Last question.
Can you infer the stellar radius of this massive star?
I didn't hear.
Can you infer or obtain the stellar radius of this
Yes, because
massive star?
these models are spherical. Okay, so you get a flux distribution, an absolute flux distribution. You get your magnitudes, and then if you know the distance, of course you need to know the distance, and then you correct for reddening, and then you match the kind of radius that multiplied by your flux makes that observed magnitude. So in the galaxy there's a problem, because for most of the stars we don't know most of the distance. We know that for the stars at the galactic center we know If you look at the LMC, you know it's 50 kiloparsecs, but many of the stars in the in the galaxy itself, you don't know if they are 600 parsecs or 1 kiloparsec away. And that's a problem. But as soon as you do the distance, you can get the radius and the full luminosity of the star.
Right. Thank you very much.
Thank you.